All right, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE318 Electronic Circuit 1. And today is our 25th lecture, and December the 3rd. And today we are going to do more exercise or say examples on the BJT amplifier circuit and AC analysis, as well as some DC analysis. And also, since the very last midterm exam happened next Thursday, so today we're gonna do also the review. Okay. Nothing special. Same pattern as the previous exam, but let's go over it. Okay. All right. Let's start our lecture now. So here, we are dealing with example 3. Let's take a look at the circuit, given circuit. Okay. First of all, we can tell base, collector, and the emitter. Identifying the 3 terminals, and then followed by identifying this is common what? Common what?
Collector.
Oh, a collector. Very good. Very good. So input is base, output is at emitter, so it's common collector. Well, of course, and the title is also telling you that, but you should be able to come up with this conclusion yourself. So this is the terminals and the common circuit. And now let's just conduct AC analysis to find a voltage gain, including R naught. Okay, the problem is telling you to including the R naught. So what you want to do is just first of all have the circuit, find a small signal circuit yourself. Okay, I will give you guys another 3 minutes, and for you to do this yourself. Okay, and then I will present a solution. Okay. If any questions, bring it up anytime you want. Okay. So okay, go ahead. 3 minutes for the circuit.
So it's just the AC part, not the DC.
Correct. Just the AC, because we don't need to really find the value of the voltage gain, since we don't have DC results, right? What we need is basically the circuit followed by equations, and then you can go ahead to find some results in terms of the symbols, R1, R2, RE, etc. All right, let's see the circuit here. At least this is the first version of your common collector circuit. All right, so this part is the small signal model you should have. Okay, this is the NPN. Okay, this is NPN. Be able to tell that. So we have this small signal model, and then we are extending the circuit terminal by terminal, right? The base to R1, R2 parallel, and also RS, and then VS. And collector is the ground. Collector here is shoot to the ground. The emitter is the output. The emitter is output. It's labeled here. Output. And also emitter has a resistor RE. The other terminal of RE is the ground. So here we go. RE is down here. So output is down here. Output is down here. So like we have ever done this in MOSFET. I drag the top part, the dependent current source and R naught, and also the collector ground, drag them down and flip it. And then we can end up with this circuit, which is easier for us to write equations, right? Of course, that step is not necessary. Okay, if you don't do that, that's fine. And of course, here also telling you, emphasizing the R naught is always between the collector and the emitter, just like the R naught is always between the drain and the source. It has nothing to do with where is the ground. Okay, it has nothing to do with that. You need to be very clear on that. And this is the circuit. Take a look. Take a look. Okay. See any questions you have. And if this is good, then go ahead for the equations. Go ahead. Okay. And of course, you need to be able to tell you having sufficient equations by counting the number of them. Okay. Go ahead. Another 4 minutes. All right, let's see the solution for the equations here, okay? So first, because I'm based on this circuit, it is very clear that I want to do a KCL. Okay? I want to do a KCL at base. And even inside of this version of the circuit, KCL at the base was one of the equations we had in previous example, right? This the example is very useful, and the KCL at the base is commonly used in these examples. Okay, so this is the KCL at the base. Next, KCL at the emitter. Emitter is here, right? In this circuit, the emitter is this kind of throughput node, and here the emitter is just here, right? Just the emitter is here. Anyways, multiple currents going in and out to this node. So we have second KCL. Yeah, second KCL. Essentially, we use this KCL as well in the previous example. Okay. And of course, we also need another equation. I don't know how many of you realize this. This is nothing but VBE equals to VB minus VE. Okay. This is nothing but equivalent to VB equals to VB minus VE. Okay, this is means this. And the VB equals to what? VB is nothing but the V in. Now we call this as V in. If you call this node voltage as V in, this is nothing but V in, because I'm using V in the previous equations. And VE is the voltage as the emitter. It's here. What is it? You need to realize VE is nothing but V naught. Okay, VE is nothing but V naught. You need to realize this. And the VBE, as you know, is V pi. And we call it VBE or V pi, it doesn't matter. So these two equations are same equation, the same equation. So what unknowns you have? We have input source Vs, V in, V pi, V naught. That's it. 4 unknowns, 3 equations, done. Okay. So take a look at this. Okay. And also be aware that these 2 KCLs and also this last equation, the VB equals to VB minus VE, they are all in our handout. They're all in our arsenal. Okay. Please check and confirm these. Okay, I checked your handout. In the procedure, the arsenal I provided include all of these weapons equations. Any questions? Any thought? Any trouble?
Makes sense.
Sure. Anyone got them correct at first place before I presenting the solution? Anyone get all of them?
Got 2, but not 3.
All right. Which one you didn't have?
Just the last one.
Last one. Okay, last one. It's actually also one of the weapon in our arsenal, actually. Yeah. Between 2 nodes, the voltage potential is actually equals to the voltage at the first node minus the voltage at the second node. Both are with respect to the ground. So this is what it's mean. How about
how you would get the KCL at the emitter if you were using the first circuit?
If you do the KCL at the first circuit here, the same thing, right? Here you have a current going into it, like this. You have second current going into it, like this. And you have third current leaving it, right? So these two currents up here, the sum of them equals to the current down here, right? And the current here is equals to what? Ohm's law. A voltage V pi divided by R pi, right? Ohm's law.
Okay, so that was just like the previous example.
Yes,
Right.
this part
Okay.
is very close. Yes. Yes, we did use the same thing, as I said, in previous example. And the current here, as you know, is dependent current, dependent source current, GMV pi. A current here is once again Ohm's law. Ohm's law. V divided by RE. V equals to V naught. So of
So what
course,
happens with
but-
R naught then?
R naught is very tricky. By this look, you are very easy to miss the R naught. However, you need to realize the R naught and the RE are parallel. So the current here is actually not equal to GMV pi. The current here plus the current here equals to GMV pi. Does it make sense?
Okay.
So when you consider this, you're considering this supernode. Therefore, essentially, how many currents involved at this supernode?
3 or 4?
No, 4, exactly, 4 current. Current flow R pi, current flow through dependent source, and current flow R naught, and the current flow through RE, right? So in the second equation, okay, we just talk about a second equation. Left-hand side remains same, 2 currents. Equals to right-hand side is actually V naught divided by R naught. V naught divided by R naught. But here is V naught divided by R naught, the current flow upward, right? How about plus V naught divided by RE? Does it make sense? So we have 1 term, 2 term, 3 term, 4 terms. That makes more sense, probably. However, essentially, V naught over R naught plus V naught over RE is equal to V naught over R naught parallel with RE. I don't know if this makes sense.
All right, yeah.
Right. So this is the same. If you cannot see R naught parallel with RE, that's still fine. You gotta end up with this equation, which is same. Of course, and these two circuits, top and bottom 2 circuits are equivalent. And then the result of the equation should be equivalent as well. Otherwise, it makes no sense. Okay, something wrong then. Okay. And it's hard to see from the top circuit here, first circuit here. Of course, otherwise, why I would bother to convert it to the bottom one, right? Top one is okay. However, it's not. It's hard to see. Okay, it's very easy to miss or not. How about others? Daniel, how are you doing?
I'm good. I had just had it confused due to the circuit differences at first. I forgot. Like I didn't realize RO was parallel to RE at first.
Yeah, for is actually once again, like I said, this is why I converted down to here, right?
Right, and
Because from
that
this
makes sense now.
Yeah, the circuit has no mistake. Okay, don't take me wrong. The circuit is fine. However, it's hard to see. It's hard to
Right.
see, and then when you write equations, you might make mistakes. Okay. How about the first KCL and the last voltage difference? How about these two?
I didn't write down the voltage difference, but like I know it's there, and then the first one I had.
Okay, that's good. That's fine. That's fine. Oh, one more thing I need to remind you guys here that the label here is a little bit tricky. You see the difference? This is nothing but equals to GMV pi. Okay. And if you don't be confused, beta IB equals to GMV pi. No problem at all. Okay. Feel free to use GMV pi. Okay. Don't bother anything different. Okay.
Isn't it important that we use GMV pi just so we can cancel out V pi?
What you mean? That's why you don't want to use beta IB, right?
Yeah.
Right. That's right. And we don't want to have something new pop up. That's right. Good discussions. Kevin, how about you? You're too quiet. I'm not used to it.
I didn't have any of them yet. I was writing them all down as I's. Like I had I did the KCLs with the I's, and I was up to like.
Well, first of all, it's not necessarily wrong. However,
Yeah.
you are absolutely introducing more complexity to yourself, right? Which
Yeah,
is
I always forget to do the one with the where it just go straight to the voltages over resistance. I forget
exactly.
I get there eventually. It just takes me an extra 10 equations.
No, we actually don't want to do that. And since we are looking for the voltage gain, right? We are looking for the voltage gain. We want to play with the voltage, right? I'm not seeing any benefit to play with current. No. Good. How about you?
I got the first equation and the bottom equation. I didn't get the middle one yet.
Oh, okay.
Yeah.
How about it now? Well, you okay. Like I said, you might end up with four current terms. That's absolutely okay. Okay. So you don't have to be able to see R0 and R0 and RE are parallel. They're probably a little bit hard to see. Okay, it's like I said several times. From this first circuit, it's hard to see. No, it's not very easy. But if you end up with four current terms, because you need to consider this guy here as a super node. You have supernodes involving 4 branches current. Okay, you're seeing this, then you're good. You need to just be careful the voltage polarity. For example, the current flows through the R0 as upward. Does it make sense? V0 is actually from here to here, V0. Does it make sense? This is the polarity of the V0 for R0. So you're using V0 over R0, or maybe you're using VE over R0, then resulted current is upward. Okay, leaving the node. These are the details you need to take care of. Okay. Good.
I have a question about one of the examples from the other day. I think it was the last one we did.
Okay, let me put that up.
It was whichever one we used VT in.
Hold on, you mean actually just the last lecture, right?
Right.
Here we go.
So I guess what I was confused about was
This one maybe?
yeah, where we were finding the parameters. How do we know what the value of VT is?
Oh, anyone knows?
26 millivolts.
Very good.
Oh, okay. So it's just the same as a
Yeah,
Okay.
except otherwise being told.
All right, gotcha.
26 millivolts. We use this since
Right in the
MOSFET,
Okay.
yeah, MOSFET and diode actually. Yes.
Okay.
And the diode, correct.
All right, that makes sense then. Thank you.
Yep, sure. Of course, if otherwise being told, you can follow the problem given then. Yep. All right. If this is good, let's move on. This one. Go ahead. Circuit and equations. All right. Let's see. First of all, the circuit. Okay. The circuit is like this, and of course, this is not first version, first circuit you're gonna receive, but you can check to see if yours is equivalent to mine. Once again, I do a conversion so that I'm seeing a very nice bunch of meshes circuit look, so that I can easily find the equations I want. Okay. Any questions? And here are the equations. Let's see. Okay. Actually, I just used 2 equations and 3 unknowns, as you know. V naught, V pi, and the Vs. 3 unknowns. 2 equations. Done. And 1 equation is actually output equation. This part, output equation, Ohm's law. Another equation is the KCL at emitter. The KCL at the emitter here. How many current terms involved? Up to 4, right? Up to 4. Or if you consider RE and R pi are parallel, you can say actually 3 currents. That's fine too. Either way, you are able to reach this equation. Like I said, this term is essentially just equals to V pi divided by RE plus V pi divided by R pi. Okay. So take a look, see any questions you have.
Where the collector and the base come from, but I'm not seeing how you get there with the emitter. Do you think you could show how you would draw that with our normal model with the emitter on the bottom?
You're talking about a circuit, right?
Yeah, I'm talking about
how we got this circuit.
Just the emitter portion I'm having trouble with.
Okay. Well, let's begin with the basic model. This is NPN or PNP?
NPN.
NPN. Okay, so this is the basic model, right? This is the basic model. The basic model, and then we start to extending the circuit of terminal by terminal. So first of all, base is like this, right? So base, the VEE is shorted. So this is the emitter, okay? And the base is down here, right? Base down here, due to the existence of CB, which is what? Bypass capacitor, right? So what is your base? Base is what?
Go straight to ground.
Ground, okay? This guy is ground. Done. And then followed by collector. Collector is here, right? Collector connect to RC and then short to the ground as well because VCC is shorted. CC2 is shorted, so RL is parallel with RC. Right? You can separate them. RC, RL, and the collector is also the output. No problem. Okay. This is the ground. Feel free to have inner grounds sketched here. You don't have to short with the base. So this is the base and collector, and the no I have no trouble with. And let's talk about the emitter. Emitter, according to here, the emitter connect to RE, right? First of all. Connect to RE, and then the other terminal RE is ground. And then the other terminal is ground. Emitter is also connected to RS. And then the other terminal of RS is VS. And also be careful, the RS series connected with VS is parallel with RE, right? Which means like this. Right? This is the emitter. This is the emitter. And of course, from here, how can you see the circuit? How can you convert this circuit to the circuit I'm presenting? Let me use the red. Okay, how I do it. This part is nice, isn't it? Don't you think? This part is very nice. We don't want to touch. That makes sense. So what do? We drag the emitter here up. If you do this, and then this dependent source gonna become what? Rotate by 90 degrees, isn't it? And also short this ground with this ground base. Therefore, R pi eventually becomes this, right? You drag the R pi down here, then short it with here. So here gonna be the base. Here is the R pi. However, be very careful. The V pi negative polarity is the emitter, so it's up here, positive here. This is V pi. So now here is gone, becomes this. Once again, negative polarity of the V pi is at emitter. Positive polarity of the V pi is the ground. And then now what are you going to do? As I said, drag this part up. Then you're going to end up with R pi, V pi, RE. No, this is the emitter. Yeah, RS, VS, positive, negative here. And then here you have a dependent source. RC and RL here. This is output. Does that make sense? And now, as I said, our RS and the VS series connected is parallel with RE. Therefore, it's also parallel with R pi. So what can you do? You can drag this branch to here. Does it make sense? And end up with exactly what I have in the slide. Does it make sense, everything? Everybody?
So I got the blue circuit got up there, then I don't know what to do next after that.
Okay. So how about now? Is it better?
Yeah, for sure.
Yeah, sure. Blue circuit is okay. However, once again, just like the previous example, it's hard to see. Okay, so you might have trouble in writing equations. However, if you don't, it doesn't necessarily mean you're gonna have wrong equations, though. Okay, so you just need to be careful when you write equations. Any other inputs? Any other thoughts?
So the way I did it is I did KCL at E and just had a
Which
placeholder
circuit? Which
VE.
circuit?
The blue one. That's
The
the,
blue
one I
one,
went
okay.
off of. Yep.
And then
And then I had VE equals negative V pi. And so
Okay.
my KCL is just a little different than yours because I had I didn't simplify it as much because I could have put R
can
pi
you
and
repeat your
RE in parallel.
KCL? Let me judge it.
Yep. So I have VE over RE is equal to V pi over R pi plus VS minus VE over RS plus GM times V pi.
Okay, let's see KCL at emitter, okay, in blue. So first of all, in this circuit in blue, so he's saying the V divided by RE, okay, this down here, it's leaving the emitter. It equals to V pi divided by R pi. V pi divided by R pi is a current entering into the emitter. So this is good. Yeah, this is good. Because this VE over RE is leaving it equals to the current going into it. And then what else? Else equals to VS, which is here, minus VE divided by RS. Very good. There's also another current entering to the our emitter. Then he has the very last current, which is GM times V pi going into the emitter. Correct. Okay, his equation is correct. Let me see. Let me see mine. This is mine. A little bit different, but actually same equation. Same equation. Because of the fact that V pi equals what? Negative VE. Okay. VE equals to negative V pi, or say. Okay. Because of this. So actually, his equation is the same as mine. Okay. It's correct equation. No problem. And output equation part, as I said, is the easiest part, right? It shouldn't be a big deal. Shouldn't be a big deal. Any questions? Any concerns?
Yeah, I don't know. I don't feel entirely comfortable switching the circuit around in all the cases. Like more that, I could see that pretty easily, but I don't think I would have been able to do this on my own, switch it around to what you had.
But based on this blue, still no problem. Can you still?
Yeah, I like that. I like that.
Can you still come up with the correct equations like Shane did?
Yes.
Then you have no trouble. You don't want to do this, then you don't have to. There's no credit for given to this step. No, it's not required step. But it's fine. It won't prevent you from receive the correct equations, which really matter. Okay. All right. So any other questions? Any concerns? All right. If nothing, then let's finish today's very last page here. So here's a summary of the basic BJT amplifiers. So in terms of gain, voltage gain, current gain, and input impedance, input resistance, or say, and output resistance. Okay, it's very important. Common emitter, the gain is greater than 1, generally speaking, and the current gain is greater than 1. And input resistance is moderate. Output resistance is moderate to high. So first of all, let's talk about the voltage gain first. The common emitter is good for what? Amplification, right? Because the gain is obviously greater than 1. So it can amplify things. Good, amplification. And then emitter follower. What does it mean by emitter follower? Emitter follower is nothing but common collector. Okay, don't be confused. And the gain is around 1. Okay, so it's not good for amplification, right? Third one, common base. The gain is decent. Okay. And in terms of input resistance, the common emitter is moderate. Common collector is high. Common base is low. First of all, input resistance is the higher the better, or the lower the better for a voltage amplifier. Anyone still remember? Input resistance. This is very, very important. Input resistance and output resistance, what we are talking about is The same idea we have been discussing for MOSFET amplifier. Input impedance is like what? Voltage divider. Output resistance or impedance. So also it's following a voltage divider principle. Input resistance of the amplifier is determining how much voltage you actually can have occupied out of the input source. So the higher the better, the lower the better. Absolutely, the higher the better. Okay. Once again, this is the idea is you have amplifier and then you generate certain voltage. And then you're trying to feed the next stage, which is obviously the load, right? This is your output resistance concept. This is the output resistance concept. The voltage of the load is equals to the generated voltage times a voltage divider, right? You want all of the generated voltage VG occupied by the RL rather than the R naught. So the bigger the RL, the better. However, you have no control over the RL, okay? Because RL is the load. It's up to the customer. So you can only control your R naught. So the conclusion is what? The lower the better. The input side, this is the output. Okay, that's the output R naught. The input means what? You have a source, right? And you have the source has RS. Then to you, you have the amplifier, you have RE. Okay. So you want your amplifier to occupy most of the voltage. V in just equals to V source. Let's say this is a VS. Okay. V in means the voltage received, really received by your amplifier, equals to source voltage times R in over RS plus RE. Similarly, you have no control over the RS. It's up to the source. So you can only control the RE. So the conclusion is the higher RE is, the better, because more voltage you can occupy. Does it make sense? And if you need more, the first time actually this semester we talked about this is lecture slice number 4. Okay. And this is a voltage amplifier model. We are seeing an input and voltage divider and output and voltage divider. This is a very, very important concept. Okay. This is the first time we touch it. Since then, we have been talk about it several times for MOSFET and now BJT. And actually, have any one of you guys in the middle or almost finished the project? Has any one of you reached there?
Yeah, I think I'm getting there. Although my voltage gain at the moment is about 200, so that needs tuned a little bit.
Your voltage gain is equals to 200, means you are not adding any load yet. Am I right?
Yeah, I think so.
That's exactly what. Okay. You have no load, meaning your RL here is pretty much infinity. Of course, infinity can occupy all of the generated voltage. And then your output voltage, of course, the gain is super big, 200. Not a surprise.
So when we attach the emitter follower to it with the load, should we expect to see numbers that are close to the 6 to 10 range?
Correct. However, if you're not attaching the common collector output stage, you are directly feeding that 200 no load gain onto the 10 ohm load. What's gonna happen? Did anyone see it? No common collector. You directly feed to the 10 ohm load. 2CE, right? 2CE directly feeding the load. Has anyone tried that? That is called so-called load test.
I tried it with one CE,
And
if I recall, I got something like -37, I think, on the first one.
with load, what do you got?
I don't know if I tried it with the load yet. I don't think I did.
You know, absolutely you didn't. -37 is a decent no load gain. I give you that. However, if you add load on it with 10 ohm load, anyone else tried it with 10 ohm load? What's the gain? It's 0.0 something gain. Okay. Of course, depending on your no load gain, you might have different with load gain. But I'm telling you, it's very tiny, way below 1. Okay. And be careful when you read the gain value. This is what I'm emphasizing. Your output resistance need to be taken care by what? The common collector. Why common collector? Now we go back to the summary here. Why common collector? Because common collector has very low output resistance. Can you see it? Very low output resistance for a common collector. This is exactly what we want. Okay, so common collector has high input impedance and low output impedance. Good, we like it. The gain is kind of doing nothing, right? However, very good input stage and also a very good output stage. Any other questions? All right. Have a good weekend. Bye-bye now.